So, as Matt said, Eladio Dieste practiced as an architect engineer in Uruguay and lived from 1970 to 2000. Most of his body of work is kind of from the 60s through the 90s. And the first question that I get asked is, why am I going to introduce Eladio Dieste to people? And that's why I start with this slide. This is, to me, kind of sums up all the reasons that I love his work. It's simple, quite minimal structures that serve a really industrial purpose. They just had a kind of pure function. In this case, this is called the seagull, and I'll explain more about it later. But it's just an elegant thing. It sits on a single column, spans something like, 56 feet by 14 feet, so I think it's something like, anyway, I'm not going to try to convert it right now. But with a single, simple, reinforced concrete and brick shell. And I'll explain all about the techniques behind it later on. So the reason I love this work is because there's a kind of elegance to its lightness. The way it touches the ground and the way it kind of talks about all you really need for a great piece of architecture is a brick roof. There are four principal areas of interest in Dieste's work. I'm going to start at the bottom here. So the one that I'm not going to talk about tonight is the folded surface, but this has resonates in a number of his projects, which is quite stunning. The ruled surface is one that is quite intriguing because it takes a very simple tool, the mechanism of the brick, and uses it to create complex three-dimensional surfaces. The cantilever barrel vault, we'll look at this quite a lot, and this is all about the cantilever because, just like the previous image, uses this to extend the space of that roof quite a distance. Consecutive because they're linked together. And then we've got the Gaussian vault, which is another complex system, and it covers an extraordinary range of structural problems with a really beautiful integration of, let's call it curvature and direction. So these are three different examples of this. So we see the port of Montevideo warehouse. So this is the Gaussian vault. This is one of the barrel roofs, consecutive barrel roofs, and this is the ruled surface of the Church of Christ the Worker. So as you can see, now in this case, this is a ribbed barrel vault. Dieste is using the idea of the undulation of a sine curve in order to produce an enormous vault. And this is just made of brick, so this is only brickwork doing all of this joy of space. And he's working in brick because that is something that is essential to the quality of working in Uruguay. So that's what they had. That's what they were good at. He's utilizing what's there as the kind of the resource, the real resource. And within it, you take a utilitarian space and you get something extraordinary out of it. You don't have to work so hard to kind of talk about the architecture because it comes through as material manipulation. In order to build it up, it's a series of really quite simple layers. And this is all using, what do you call it? Very straightforward labor techniques. Scaffolding, rough scaffolding, leading up to a surface that is laid over with simple timber slabs. And then you start to lay on the brick pattern, and then it gets reinforced and laid with another layer of concrete. And what you get out of it are these complex shells which start performing whether it's bandstand or it's protective structures. Produces a space of architecture that is astounding, lightweight, and something that's quite surprising. And so what we're looking at again is the scaffolding that's going up inside it, the scaffolding work that's going to be used for the laying of the brickwork, the actual inside shell, and then going back in and patching into it from below to produce these wonderful forms. So now we're going to start talking about the consecutive barrel vault. So as you can see, this is an industrial piece of work, right? These are just toll booths. This is just going through from one parking lot to the next. And it's got this simple barrel vault coming down onto a single column in the middle, and then balancing themselves so that they stretch out and they produce this wonderful shadow in the harsh sun of Uruguay. This is stunning to me. It's like something that all you need to provide great architecture is a big roof. You can produce a huge amount of roof just by this elegant 150 mil thick plate of brick and concrete. And this is how he builds it up. So being an architect engineer, he worked out a method to say, okay, well, we've got our stratum here at the very bottom. We're going to start laying up our bricks. In between the brick, at the bottom of the vault, we're going to lay these stressing cables, reinforcing cables. In between each line of brick, we're going to lay these stressing rods. And then, as you build up, you put on the layer of concrete. But on top of it all is wrapped this set of reinforcing bars. You can see it here before being stressed. And he pulls it together at the center. And what it's doing is it's post-stressing that entire cantilever so that it starts lifting itself up and giving itself the ability to span such a wonderful distance with such minimal amount of material. Material effort is maximized in this case. So you can see the section is 150 millimeters. It's a brick with the reinforcing cable going through, being looped back up, and this is the upper tie. This right here is the upper tie, which is pulling that whole system back into tension. I think this is incredible. Like, with very minimal amount of material, you can produce an extraordinary effect. And as I said, these are really industrial. These are municipal bus terminals. These are for train stations. This is producing space for the working of the city. To extraordinary delight. I think that's the nicest part about it. It's not just I'm going to provide a big roof. It's not just I'm going to make a utilitarian structure, and because I want it to be overhung, I'm going to produce this enormous structure that will cantilever this huge truss. You truly believed in understanding the essence of the material in order to produce something without force, without kind of trying to power their way through the mechanism. And one of the things that I want to talk about next is actually this element here, which is just the end column and this flange, because all along, all of these barrel vaults are actually acting against each other. So as they press down, they're balancing each other because the next one is in sequence. But when you get to the end, all that force wants to then push out. So it says, no, I'm just going to extend the length of that edge, the width of that barrel vault by making this flat plane and down stand, and we'll just gently touch that column and structure everything that you need. So this is what it is in detail. That barrel vault is coming around. All those forces want to push up this way, and it extends the edge of that barrel vault horizontally and then down back to touch the column in such an elegant and fine way that it achieves something that kind of would take most engineers and architects to kind of brute force to kind of put a huge structure there. I mentioned before about the kind of the reason I love this work is because it can span with such a lightweight structure. It can span such a great distance. To give you an idea, let me see. Maybe I'll use this example next. Some more about you get in section space. One of the other things that he does is he looks at it in layers. So he doesn't just use it as a kind of single dome, a single cantilever vault, but he actually uses multiple layers of it and allows them to slip past each other. So now you get that space of light in between for free. You get the space of overhang for the train stations, so it protects the trains as they land, gives a space for kind of the train to kind of sit underneath it out of the hot sun, and is cantilevered back over the actual stop. So we're back to the seagull. So in this case, so it's 17 meters in length and it's 5.4 meters in width. Now, to get an idea of that, if you wanted to do a beam that could span the same distance, 17 meters, it's a pretty simple calculation. It's really about, it's L over 20, right? So you you say 17 meters divided by 20, so you've got an 850 millimeter deep beam to do this. So that would be the beam, the typical beam that you would need in order to do this same thing. It's producing a type of extra structure through curvature. So the idea that you can just produce thickness through form is the kind of essence of being able to post-stress all these constructions. Now, this was built for a petrol station. And I love, it's a utilitarian structure. And the city loved it so much that they moved it, and now it marks the entrance to the city. So it's part of the city. It's not something that's kind of then gets thrown away just because it's, well, no longer in use as a petrol station. It's something that actually is a kind of marker for the city. And again, really utilitarian, basic structures, simple things that help the life of the city. Toll stations and bus stops. And keeping in mind the environment, these simple roofs protect the building. They extend a long way out and offer a lot of shade and protection for these warehouses. But then you get into the kind of examples where he starts to combine the effort of the ruled surface, which is, all he's doing is he's got a straight line down the bottom, and he's got a sinusoidal curve at the top, and starts to link those two. It's a very simple move, but in doing that, it starts to not say that you don't have to have a kind of super thick wall. He's using the geometry of those curves in order to structurally thicken that wall. But this goes one step further. It also has a set of barrel vault roofs up at the top, not the same way, but a different kind of barrel vault roof that's forming the inside of this church as well. So you can see straight line of the ground, and then this is the sinusoidal curve at the top. Really elegant church. You can see here's this section, which Jonas would say is too thin. I disagree. I think so. So we had just talked about the section earlier. This, normally you see a section drawn that thin. It's kind of like missing a certain amount of material. What my argument is actually the structural thickness, the structural depth of this roof is actually this much, but the material depth is minimal, and that's what's really so elegant to me about much of this roof. And these are the men starting to build up the roof, or sorry, to build up the walls. This is the diagram showing how the stresses are going to be played out through when it gets to the top of the roof. This is the bottom of the barrel vault coming this way. So this is the reinforcing coming through the roof, stretching into the walls and peeling along, so you see the wall itself thickens up and actually has a little bit more depth to receive those this reinforcing work coming through it. And in a really loving way, they complement each other, both roof and wall. And what you end up with is this wonderful undulation, and from the inside you start to see the undulations of the roof. One more construction stop. And then you get it from the inside. So now we're seeing the undulations from the inside, and then the undulations of the roof, where you see this part of it is higher, and this part where the wall is coming in, you've got the lowest edge, the low chord of the undulations of the roof. And it also allows them room to kind of set things free. So in this case, it's creating a wall which is a series of kind of slats of brick. And so this is really quite an extraordinary church. I think it's one that's very difficult to comprehend just how much remarkable engineering went into it, because it's such a simple and modest structure. And likewise, he did the same sorts of moves with this one. But I'm more intrigued by, you'll see in the next image, what he does with this, with the kind of tower behind. It's very similar to, in terms of using the ruled surface and the vaulted roof. But then at the end, you see that the roof starts to peel up. This is now looking up the tower, and it sails up inside, and you get this whole other experience looking up that tower at the end. So now the third set of ideas in Dieste's work is the Gaussian vault. So the barrel vault is very simply just an arch, right? And it comes down, and you've got then a reinforced bottom flange. In this case, where he's extending the idea of the barrel vault, but he's looking at ways in which you can take a big structure, like warehouses. So once again, that's the Montevideo. It's another one of a fruit warehouse. You can start to see that he's able to start to produce light within the structure by looking at how to curve in section this this roof. I always love trying to draw this. This is my kind of quick sketch of it. It starts out at the edge as a flat line. So it's flat line, the two edges. And then in between, at the middle section, it's got this sinusoidal section to it, right? So it's got an S section to the whole vault. In addition, it's vaulting, or it's arching from side to side. So this has a very long span with actually quite a low height, it's only 6 meters height. But because of this wonderful twist in the way in which the brick and the concrete are formed, he's able to produce that much more structural strength to it. So he's adding structural strength by giving it a form, giving it a geometry. And then again, you can see that he's clever enough to start to look at how by extending the edges, he doesn't have to think of these things as having to be buttressed by big walls, but he can actually use the form of the roof to stiffen the edge. So you can actually, within the form of the roof, you can actually produce the structure. You can see these are massive buildings. This is kind of wonderful how big a set of buildings you can produce with this very effective, very efficient mechanism of construction. So here you see the section of this Gaussian vault. So the simple S curve, you can see it's convex and concave. And so there's a midpoint here where it's actually the inflection going from one curvature to the other. And that's its cross-section in order to produce that kind of extra structural depth. I find that this work is quite inspirational because it produces a huge amount of space with a kind of minimal amount of material effort. And he's going about making kind of architectural engineering through the excitement of saying, oh, now I can let light in, I can set space free, I can do things with a minimal amount of effort and maximum effect. So that's Eladio Dieste.